5.3 focuses on how can we improve the estimates of the integrals using this type of smart algorithm that can estimate the error without having to find any derivatives. So this basic algorithm is called Richardson extrapolation, and kind of the highly efficient way of doing it that we're going to present in this lecture is called Romberg integration. So the basic concept is to combine two estimates and get a third better estimate using a combination of two less accurate kind of estimates. Okay. So what we're going to do is try to derive that equation first to look at how can we look at the error without having to actually derive any derivatives. And the way it's done is basically using two estimates at two different step sizes using the trapezoid rule. So in general, when we're estimating an integral, our goal is to find the true value, right? So I here would be the true value, and this would be equal to the estimate I at a specific step size, h, right, plus the error involved in this method that we're doing at the step size also h. So here we have the exact value of the integral. Then here we have the estimate of the integral at step size h. And here we have, we can say, the truncation error for that method. So what we're going to do is we're going to have two separate estimates, right, with two different errors. And then we're going to try to find what's the ratio in the truncation error for the two different step sizes using trapezoid rule. Okay, so two separate estimates with two different step sizes, and basically they're going to be h1, where h1 is going to be usually the larger step size than h2. All right, so looking at this equation up here, right, the only true or only repeated value between h1 and h2 would be I, right? So what we're going to write here is I, the true exact value for the integral, is equal to I, right? And then on the left side and the right side, we're going to write down two equations where one is for h1 and one is for h2. So on the left side, I'm going to write I h1 plus the error equals to I at h2 plus the error h2. Then what we're going to do is look at the error equation for the trapezoidal rule and find what's the ratio between EH1 and EH2. So looking at the trapezoidal rule, so for trapezoidal, the approximate error, right, is equal to negative b minus a to the power of, I guess, nothing in this case for trapezoidal rule, and h squared f second derivative or average second derivative. If we are changing the step size, right, h1 and h2, does the second derivative change? The average second derivative? Remember, it's like the integral. Yeah, there's no h in that equation, so it doesn't change. So what we're going to write is assuming, the average second derivative is constant. We don't need to assume that it's actually constant because the span a to b is constant. So the average that we're calculating for both will be the same, regardless of step size. So in that case, what do you think the ratio of EH1, actually let's use purple here, What's the ratio EH1 over EH2 in this case? What do you think that's going to be equal to? So what part of this equation stays the same and which part changes? Only the h, right? So then the ratio between the two errors is simply h1 squared divided by h2 squared. So you can see by doing this, we've eliminated the second derivative. And then what we could do is rearrange this equation, right, to solve for one of the errors. So in this case, we can solve for EH1. And that's going to equal EH2 times H1 squared divided by H2 squared. So now I can take this and plug it in here and then solve for what's the error when I have a step size of H2, right? And if I know that error, then I can plug it in to this part of the equation and find what's the true estimated integral, because we are still estimating, the error, it's not exact. All right, so let's plug it in. So we're basically taking this equation here, right? And we're plugging in what EH1 is. So we have IH1 plus EH2 now times H1 squared divided by H2 squared equals IH2 plus EH2. And then now we're going to rearrange to solve for EH2. So that will give us IH1 minus IH2 divided by 1 minus H1 divided by H2 squared, which is the same as H1 squared divided by H2 squared. Now we can take this and plug it in, right, to what is the true value of the integral. So again, just to kind of note here, this is an estimate, not the true error, okay? So it's the estimate of the error. All right. So I equals IH2 plus EH2 now becomes IH2 plus IH1 minus IH2 divided by 1 minus H1 over H2 squared. So now we've come up with an equation, right, for the integral that includes an error term which does not require any derivatives, right? And it should be more accurate than what we've been trying to do, but it requires two estimates, one at H1, one at H2. So the order of error in this case for this equation would be h to the 4, while the trapezoid was h2 or h squared. So here, order of error is h to the 4. Now we're going to look at the special case where h2 is half h1. In that case, we can derive a simple equation and then just use it in problems. So if h2 equals to half h1, so h1 divided by 2, then the above equation becomes I equals 4 over 3 IH2 minus 1 over 3 IH1, where IH2 would be more accurate or less accurate than IH1. What do you think? Which one has the smaller step size? right? So then that one would be more accurate, right? So this here typically will be the more accurate estimate, and then this would be less accurate. So the notation will change later on in this lecture to, instead of writing IH2, we were going to write, IM for more accurate, and then IL for less accurate. But I'll also define it again later, but I'm just letting you know, like, that's what's coming. All right, so we'll do an example using this method. Again, this example is going to be skipping the trapezoidal calculations because we've seen those, and we'll go straight into, how can we apply this equation? And not only that, this is considered first iteration Romberg. There's actually a second iteration Romberg as well. So example, we're going to use Richardson extrapolation to evaluate the integral from 0 to 0.8 of the function 0.2 plus 25x minus 200x squared, 675x cubed, minus 900 x to the 4 plus 400 x to the 5 dx. All right. So what we're going to do is basically set up different step sizes. So for the first one, okay, we'll do h1 equals to 0.8. So that would be basically one segment from 0 to 0.8. Then I'm going to take half of that. So h2 is going to equal to 0.4. So now I'm going to have two segments. And then I'm going to take even further. Why am I doing this third one? Because I want to show you the second iteration of the Romberg integration, which we still haven't seen. So half of 0.4 is 0.2. And in that case, we're doubling the number of segments. Okay, so instead of 2, we're going to have 4. All right, so we've seen the application of the trapezoidal rule, right? So I'm not going to show that right here. I'm just going to simply write the integral when h is 0.8, right? Or when h is h1, right? So I'll just write h1 is equal to 0.1728. The true percent relative error in this case is 89.5%. So quite a bit off. Integral using trapezoidal rule with step size 0.4, which is h2, you get 1.0688. A bit closer to the true value, 34.9%. And then this third one here will get you to 1.4848, which is 9.5% accurate. So out of all these three, the most accurate is the third one, and it's still 10% off, right? So we're going to see how we can apply this Romberg integration, all right, to get a more accurate value. So in the first one, okay, we're going to use the first 2 points because you only need 2 points. You need h1 and h2. One more accurate, one less accurate. So in the first one, we're going to combine these two, all right? And we're going to call this IA, okay? So this is going to equal 4/3, right? IH2. Another thing I want to mention here, which I noticed in the past some students messed up, when they looked at the equation sheet and they wrote IH2, they multiplied this by H2, okay, then did the math. But that's not correct, right? So, right, exactly. So this is like a function. The function is I, and the value using that function is H2. So you only enter this value here. Minus 1/3 IH1. So in this case, we're just going to use the values we see up here. So 4/3, 1.0688. And what you can see is when we multiply by 4/3, we're going ahead. Okay, we're not going in between. Minus 1/3 IH, or sorry, the value for IH1, which is 0.1728. So you do this math, and you get 1.367467. Relative error, 16.6%. So better than these two. And we used those two, right? We didn't use the third one. Let's say we use the more accurate two, so 0.4 and 0.2. So this is going to be called IAB in this case. And we're going to use these 2 points, right? H3 is the more accurate, and H2 is the less accurate. So we're going to do again 4/3 IH3 minus 1/3 IH2. You plug in the numbers, you do the math, you get 1.623467. Relative error, 1%. So you went from a maximum accuracy of 10%, right, all the way down to 1% by applying one simple calculation without having to do so many segments, right? If I want to do a more accurate estimate, I would have to do even smaller segments. I mean step sizes to get more segments and more segments, requiring more computations, right? All right, so now we're going to look at how can I use IA and IB to get an even more accurate estimate. And that's considered second iteration Romberg. All right, so we can combine IA and IB to get a more accurate estimate with an order of error h to the 6. So we went from trapezoid is h squared, then one iteration of Romberg, h to the 4. Now it's h to the 6. Okay, and as you increase the iterations, it always increases by 2. In this case, the equation is I equals 16 divided by 15 times the integral, which is more accurate, so I'm going to call it IM, minus 1/15 IL, where L is for less accurate. Okay, so this is, again, more accurate integral, and this is less accurate. All right, so just applying this equation on the values that we see here, this one, 1.62 and 1.36, okay, let's see what we get. So we're going to write I equals 16 divided by 15 times 1.623467, right, what we have up here, minus 1/15 times the other one, which is 1.367467. Do the math, you get 1.640533. Guess what's the estimated error? 0%. So we got an exact value. So in general, there's an equation for, the iterations. If you notice the pattern here, this is 4/3, this is 16/15. Okay, so the numerator is 4 to the power of something. So 4 to the power of 1 is 4. 4 to the power of 2 is 16. Then the denominator is basically whatever value you got minus 1. So if it was 4 minus 1, 3. 16 minus 1, 15. All right, so there's a general equation for the Romberg integration. So the general equation or expression, which is the Romberg integration algorithm, is going to be ijk is equal to 4 to the power of k minus 1, where k is the level of integration, times the more accurate estimate, which is going to be called j plus 1. And then here we write the level kind of integration, so k minus 1, and minus just the less accurate one, which is going to be just j, and then k minus 1 divided by 4 k minus 1 minus 1. All right, so this is the Romberg integration algorithm. And again, this is, the more accurate estimate, and this is the less accurate. And the k here, k is the level of integration. So the first level is second level when we're doing Romberg. If the level is just 1, it just means I'm using trapezoidal rule, and that's it. So when k equals 2, so if k equals 2, then we get, I equals 4 to the power of what? 1, right? Because k minus 1. So 2 minus 1, 1, times I, which is, in this case, just j plus 1, and then we're going to put 1 here for the level, kind of, or the order of the iteration number, which is first iteration, minus the less accurate, so j, again, iteration number 1, divided by 4 to the 1 minus 1. You expand this out, you're going to get, 4 over 3, I more accurate, minus 1 over 3, I less accurate. Okay? So if you're doing k equals 1, it's basically the original. Okay? We're not actually doing any iterations of Romberg. It's just the original trapezoidal rule. And the order of the error is h squared. K equals 2. We're doing first iteration. I'll just say first iteration. Order of error, h to the 4. K equals 3. Second iteration. Order of the error, h to the 6, and so on. So now I'm going to do an example where we go to the third iteration, just to kind of show you how it looks like. All right, so let's do an example. Put some space here of Romberg integration. And then after that, I'll give you guys some time to try a problem as well, another one. So using the same equation that we've been looking at, we're going to use a step size of 0.8, half of that 0.4, half of that 0.2, half of that 0.1. And what we're going to do is apply the trapezoidal rule. So this one here is just, I trapezoidal rule, where, the order of the error is h squared. Okay? You're going to get 0. Let's just erase that here. 0.172800. Then if I use 0.4, I get 1.068800. If I use 0.2, I get 1.484800. And if I use 0.1, I get 1.600800. So now we can go to the first iteration, right? Where the order of the error is h to the 4. Okay, so this is first iteration. And the first iteration requires 2 points, right? So we're going to use the more accurate, the less accurate, and combine them using the equation. Which equation? K equals 2, 4 over 3 IM minus 1 over 3 IL, right? So this is kind of the IJK equations, all right? So here we get a value of 1.3674 4, 6, 7. So we saw this in the previous example, right? And we also saw this one where we combined these two and we got 1.6. I don't know actually if we saw this one. 2, 3 actually. No, this is wrong. 2, 3, 4, 6, 7. And then if I combine these last two here, I get 1.639467. If I move on to the second iteration, right? So k is going to equal to what? 3, right? So now we're going to have 4 to the power of what? 2.
Oh, 2.
Right?
Yeah.
So 16 im minus il divided by 15. So you apply that between two of these, and im would be the more accurate. You get 1.640533. Okay? And this is actually the exact value. So here we're doing order of error to the 6, and this is second iteration. Right? If I apply the next two equations, I mean the next two values, what do you think I get? The same, right? Because it's already exact. So this is the same. And then if I go to the third order, which is h to the 8, just to show you the equation, it would be 4 to the 3 in this case, where k is equal to 4. And this would be 64 im minus il divided by what? 63. So in this case, we get the same value again, 1.640533. And in this case, you know, this one and this one and this one are all exact values. Any questions? So I'll write down the practice problem so you guys can try this out. Again, this problem I'm not doing on the board. Okay, so the integral in this case is 0 to 2 ex sine x divided by 1 plus x squared dx. Okay, the true value in this case is 1.94013. So you should get a number, you know, close to that. And I want you to do up to second iteration. So if you're doing up to second iteration, it means you need how many points? 3 points. Because you want to get to this, right? So that means you need at least 3 points. So just a reminder, the trapezoidal rule, right, is a to the b f of x dx equals to h over 2 f of x naught plus 2 times summation I equals 1 to n minus 1 f of xi plus f of xn. Okay, this is just a side note. Okay. So practice this because it will show up either on a quiz or the final. Okay.